All right, number 14. Which statement describes the gravitational force and the electrostatic force? So gravitational force will always be attractive. It's an attractive force by virtue of having mass. Whereas electrostatic force is either attractive or repulsive. And it's based on charge, whether the sign of your charge. If you're two opposite charges, you attract, opposites attract, but likes repel. Positive and positive or negative and negative. Okay? So we're looking for the choice that best represents these definitions. Okay, so, and the only one that fits is choice 2. Okay. Number 15. An electrostatic force exists between 2-point charges, separated by that distance. As the distance decreases, what happens to the force? Oh my god, this is not even a calculation-based question. You just got to know relationships. You could even look at it based on the equation. We're focusing on force and the distance between them, r. So if you notice, r is in the denominator. It has an inverse square relationship with F. Okay, so that means if you increase R, the force will decrease as a result, exponentially. So now, but the question is wondering what happens when you decrease the distance. Then you'll increase the force. If you bring them closer together, think like two magnets, the force you'll feel is stronger. So these are two positive point charges. They're going to repel even further. Repulsion between the two charges increases, and that's choice 4. Number 16, let's talk about modern physics. We're going to need the reference table. So what is the energy of the photon when the electron drops from energy level F to energy level B? So I'm going to pull out the reference table in a bit. All right, so we're focusing on Mercury. That's the one on the right. We're going from F, so negative 2.68, to B, negative 5.74. We need to take the difference between them. The signs don't really matter, to be honest. We just need how much energy there is. So negative 2.68 minus a negative 5.74, and you should get 3.06 electron volts. And that is choice 3. To figure out how much energy is required to go between levels, you just take the difference between them. That's it. All right, number 17. Let's talk about waves this time. The observer counts 4 waves every 10 seconds. We're looking for frequency. On the reference table, they give you this. But that's if you have the period and you could get the frequency, and vice versa. But we don't have either. So we got to think about it differently and go by the definition of frequency. And that's the number of waves or cycles or oscillations or vibrations per second. And in our problem, they give us 4 waves completed over 10 seconds. What is the frequency? And that is 0.4 hertz. Choice 1. And finally, number 18 on this page. Copper is used for electrical wiring. We're looking for metal that conducts electricity better than copper. So all these materials of the metals are determined by their resistivity values, okay? So the higher the resistivity, okay, that leads into low conductivity. Whereas lower resistivity values lead to high conductivity. So we're looking for something that's higher conductivity. So it has to have a lower resistivity than copper. So I'm going to pull up that table in a bit. As you can see, copper has a resistivity of 1.72. And so we're looking for something that's lower than that. and that's silver. Silver is going to have a lower resistivity and therefore higher conductivity. And so it's choice 4 for number 18. Alright, number 19, a motor does 20 joules of work accelerating the block vertically upward. The block's gravitational potential energy increases by 15 joules. We're looking for the kinetic energy. So work is 20 joules, potential energy is 15 joules, and kinetic energy we don't know. How much does it go up by? So when you do work on an object, okay, so you do a work of 20 joules. That energy is going to change into different forms. So we know that it becomes potential energy of 15 joules. So we're figuring out what happens to kinetic energy. How many joules of that? So work is your total amount of energy you're putting into this other object and becomes other different forms. Since you're accelerating it upward, you're going to have an increase in kinetic energy. Okay? It's not slowing down. And since we're raising it up, it becomes potential energy as well. And so if we start with a total of 20, and we have 15 as potential, that means 5 is left for kinetic energy. Number 20. When only one light bulb blows out, the rest of the bulbs go out. The lights in the string must be connected in series because they all share the same pathway. That's the opposite in parallel. They're not dependent on each other in parallel, but in series they are. So that's why when one goes out, the rest of them do. Now number 21. An electric toaster is rated 1200 watts at 120 volts, looking for total energy for 30 seconds. So make sure you get everything down. Power, 1200 watts. Voltage is 120 volts. Energy is what we're looking for. We don't need all that information because work is just power times time. So 1200 watts times 30 seconds, that's 36,000 joules. And that's choice 4. Choice 4 is the answer. Be careful, it's not choice 2. That's 3,600. Number 22. The rate at which work is done, that is power. That's always power. Lifting this object with that speed. So power is what we're looking for. Speed is 5 meters per second, and the mass is 35 kilograms. When dealing with velocity, the only equation that fits is power is equal to force times velocity. Since we're lifting the object vertically upward, the force is equal to the weight. Okay? So we're going to take the mass, multiply it by 9.81 to get the force. And then we're going to multiply it by the velocity to get the power. And you should get about 1700 watts as your answer. Choice 1, somewhere close to there. And then number 23, just know conceptually that waves only carry energy. No mass, nothing else, just energy. It's traveling energy. That's all that waves are. Alright, 24. Glass may shatter when exposed to sound of a particular frequency. This phenomena is an example of what? So since we're talking about sound, we can eliminate anything dealing with light, and that's 1 and 2. Refraction and diffraction mostly deal with light. You can have diffraction with sound, but we mostly talk about it with light. So we're down to resonance and Doppler effect. Doppler effect in actuality deals more with moving sound source, whereas resonance talks about two objects vibrating at the same frequency. Okay, and so the one that best resembles this is resonance. Because in this case, the glass and the air are vibrating together at the same frequency, which causes the glass to shatter. And that's resonance, transferring energy between the air and the glass to cause the glass to shatter. All right, number 25. Which waves require material medium? Those are mechanical waves. Oh my god, my handwriting's sloppy. Mechanical waves. Example of that is sound. All the other examples are types of EM waves which you can find on the spectrum on the reference table. Number 26, which type of oscillation would most likely produce an electromagnetic wave? We can't talk about 1 because that's like sound. 2 is mechanical. 3 is also mechanical, and the one that best fits is choice 4 for electromagnetic wave, thinking about light also. So that's another key word to think about. Number 27, if monochromatic light passes from water into air with an angle of incidence of 35 degrees, which characteristic of the light will remain the same? Okay, so when light refracts between two materials, direction changes, clearly as you can see. The speed also changes. The speed and the wavelength are all dependent on the medium. Frequency is the only one that doesn't change based on the medium. Frequency helps determine the type of wave. Alright, number 28. Now, talking about that in the same light, can't get it, we're talking about light anyway. So anyway, we're going from X to Y. The index of refraction doubles. It doubles. Okay? So index of refraction, the smallest number you get is 1. When you increase that, you cause the speed of light to decrease. Because when you're at the smallest n value, air and vacuum, that's 1.0. As you increase it, then your light slows down. The speed of light slows down. So as we double that, then the speed of light will be cut in half. Alright, number 29 is tricky. And we start with a transverse wave traveling along a rope. The wave is moving to the right, and the fact that it's transverse means the particle is only going to vibrate perpendicular. That means up and down. The particle can only go up or down. So 3 and 4 are not the correct choices. Since it's moving to the right, this part of the wave has already passed point P. The one on the left hasn't, which means point P, as it goes through, the wave goes through, this part of the wave will have to go through P, and P has to follow that path, okay? So if we imagine going up and down the wave, point P will go up to follow this path of the wave that has yet to go. So it's choice 2. Number 30. Here we have an isolated conductor of unknown charge placed near a positive charge. And we have this as our mystery. But it's attracted. Opposites attract. So there's got to be some negative charge there. But not so fast. Neutral objects can also be attracted to charged objects. Okay? They have a mix of positives and negatives. Okay? They can rearrange themselves from side to side. And so here, that's how a neutral object can be attracted to a charged object, especially towards a positive charge. The negatives will go to the side closest to the positive charge, okay, like so. And that's how number 30 can also be choice 4. Number 31. The quarks that compose a baryon may have charges of what? So this is on the reference table. Baryons are composed of 3 quarks. Quarks can only be positive 2/3 in charge or negative 1/3 in charge. So that's choice 1, as you can see on the reference table. Alright, number 32. Here we have a rubber block weighing 60 newtons on a horizontal surface of dry asphalt. We're looking for the minimum force needed to get started, and because it's at rest, this is at equilibrium. So the force of friction matches the force we need to overcome. Or rather, the force of friction is equal to the force we need to push it just to overcome friction. Anyway, I'm losing my mind. Okay, so force of friction is equal to mu times the normal force. Normal force is equal to the weight of the object, and that's 60 newtons. But we need to know which mu to use, so that means we have to look at the reference table. Alright, rubber on asphalt, it's dry, so we have to use static because it's not moving. We use kinetic if it's moving already, but since it's not, we use static. So our mu is 0.85. So it's basically taking 85% of 60. And that is 51 newtons. Choice 3. And number 33, which object has the greatest inertia? Inertia is just related to mass and mass alone. So that means choice D has the greatest mass and therefore the greatest inertia. And now we finally reached the last 2 pages, the last 2 questions of this part. Whew. A section can be mentally grueling just because there are 35 straight questions of multiple choice here. And that's just the beginning, guys. Okay. Anyhow, here we have a neutral electroscope. That means positives. Ooh, where's my marker? Pick a different color. Okay. Positives and negatives exist throughout. When you bring a positive rod to it, the negatives are going to be attracted to the top. Okay? So that leaves the positives to be down to the bottom. They're being repelled to the bottom. And because both of the leaves have positive charges, they separate because likes repel. They repel each other. And then when you remove the rod, the leaves settle back, which means they're back to its neutral form. Okay, just like in the beginning. So it's back to the neutral form. Negatives and positives, negatives and positives. So we're talking about the movement of the electrons here. So these are those negative charges. So we're talking about the negatives. The negatives start out somewhere in the leaves, and they go to the knob, and then they go back down to the leaves, somewhere interspersed throughout. And that's choice 3. Got to read this carefully. Alright, number 35. We need to measure the current in a resistor. So that means current, we have to use an ammeter, represented with A in a circle, so 2 and 4 are not correct. And to measure current, we got to put this in series. It must be in series. Voltmeters go in parallel. So the only one that fits is choice 1. It's the only one with an ammeter connected in series to the resistor in order to measure the current going through it. And that's the end of part A. After this is another series of 15 multiple choice questions for part B1, and then the remaining 35 free response questions for the test. Alright, now stay tuned for the rest of the videos.